let's talk about the depletion of freshwater resources. Freshwater is everything. As terrestrial organisms, we completely depend on it. Every plant, animal that lives outside the ocean needs fresh water in order to survive. Now, as humans, though, we don't just drink water. That's about 10% of what we do with the fresh water we have access to. About 70% of what we do with it is irrigate crops. So let's be very clear. What humans in the world today do with fresh water is we put it on plants in order to grow food to feed this burgeoning human population. So this this 70% or so of the water that we have access to is critically important because without it we don't eat. It's not that we're drinking it, we're eating this water. Okay. Now, let's just talk about water in general. So, here's an energy budget for the world, and you probably do need to know this for the test. So, if you take all the waters, if you look at the Earth from space, what you see is it's blue, it's water, right? Well, 97% of the water on our planet is contained in the oceans. 97%, at least 3% that is non-saline fresh water. Now, of this little slice here, this little 3%, about 80% of that is caught up in glaciers and ice caps. Okay. That leaves to, and then about 20% of this is in aquifers, in groundwater bodies. And that just leaves this little tiny sliver here that's left over, talking like 1%. And of that, that's what makes up our lakes and our soil and things that are inside our body. So really, we're talking about a tiny fraction of a tiny fraction of the water is what we actually are using to grow our crops. And of that water, we're mostly using it for agriculture. Because here's another way of breaking it down. And you're going to notice everybody gives slightly different numbers, but that's okay. It's the big picture we're looking at here. Okay, ready? So if this is the world's water, the vast majority of it, about 97% of it, is salty. It's saline water that's found in the oceans. About, let's just say 3% of it is fresh water. Now, if we take this 3% of fresh water and look at how it's divided up, about 70% of that is glaciers and ice caps, and about 30% of it is groundwater, and about 1% of it is fresh water, all right, on the surface. So that means water that we have direct access to without pumping it out of the ground. Lakes and rivers. That's a very small amount of a small amount. And then if we take this, what we find is most of this is actually part of the permafrost in the tundras. And then about a fifth of it is in lakes. And look at this, just less than 0.5% of 1% of 3%. That's every river on the planet, including the Nile, the Amazon, the Mississippi. So rivers, when we think of fresh water, we often think of rivers and lakes. That's really not much of the world's water budget. And yet our lives completely depend on it because without it, we can't grow our crops. So yeah, I already talked about that. Okay. So it's worth noting, though, that irrigation is not the norm, really. All right, okay. Most people in the world live in developing countries, so most of the farmland that they have access to is they can't irrigate it. So it turns out that really, about a fifth of the farmland in the world is actually irrigated. But of that, over a third of the world's food is produced in about 16% of the world's land. So, and why? Because, well, irrigation provides water and photosynthesis doesn't happen without water. So if you want productivity, you need water, hence irrigation. So, and people have known about irrigation forever, right? I mean, the ancient Egyptians, the Babylonians, like everybody understood, one of mankind's first big inventions was irrigation. Remember, when we studied human population, that first bump we saw in the human population curve was the discovery of irrigation because suddenly there was more food available. Well, so let's talk about where we get it from. So sometimes we get it from aquifers, and you should know what an aquifer is and how they operate. So an aquifer is just a term that refers to a water-bearing body of rock or soil underground that has groundwater in it, and that it has to by nature be permeable and porous. In other words, it has to have pores that contain water and be permeable. In other words, water has to be able to flow into and out of it for it to be considered an aquifer. So it's an underground water reservoir that is existing in the pore space of a permeable rock or soil. All right. And so we can see here, it could be what we call a confined aquifer. That means, so it just wants to flow into the pull of gravity. So it wants to move down. So here's a lake, and we have some sinking water sinking out of the bottom of a lake. It's going in. Now here's some clay. It can't move through this, so we call it a confined aquifer. It's under pressure. And now here we have an unconfined aquifer, where we have what's called a water table. So this thing is like a sandy soil that goes from here all the way down to the clay, and it's just got water filling it up to here. And now this water will flow downhill, and eventually it will recharge this lake. All right. So that's the idea of groundwater, slowly moving through these pores in the rocks. And we can build wells in it and pump water out of it and have access to water in a place where we don't have any surface water. So the two critical terms when we talk about aquifers is recharge and discharge. Not a hard concept. So recharge means the rate at which water is returned to the aquifer. Generally speaking, this is going to be through the process of infiltration. So when it rains, okay, this isn't the best diagram, but okay, these are arrows. Okay, so when it rains, water comes down, and it looks like carrots, but it's not carrots. This is water infiltrating. So here's our water table. The water table is just the top of the aquifer. So from above here, there's air in the pores, air and water in the pores. But below the water table, it's only water, okay? And groundwater, like surface water, it flows downhill, okay? And it will come out, and it will basically recharge the stream. But when we talk about the aquifer, recharge is the rate at which water flows in. See recharge right here. And discharge is the rate at which water flows out. So if I pump this well, I'm removing water from here, so I call that discharge. So the water from this can discharge into a river, into a lake, or it can be discharged up a well. But the bottom line is water in, recharge, water out, discharge. Now, aquifers become depleted when you have a situation in which the amount of discharge exceeds the amount of recharge. You're going to be a genius to figure that one out. If you're taking water out faster than it goes back in, you're going to run out. Okay, and this happens sometimes. It happens quite frequently. Actually, most of the world's important aquifers are in danger of this because it's easy for people to put more and more demand on the water, but it only infiltrates at a certain rate. In fact, with global climate change, it's often infiltrating at lower rates as the planet gets warmer and drier. Now, the place we find aquifer depletion to be the greatest problem is when we farm in areas that are fairly arid. And this is actually a very common practice. Arid lands are good because they get a lot of sun, right? And so people found it's like, well, this land seems useless, but guess what? You put water on it, and all of a sudden you can grow lots of things. So this would be central pivot irrigation systems. It looks like something from outer space. You see this in the state I come from too. You can tell that the land area here is very dry. Now the idea is, if it's dry, what's not happening? Recharge. It's not raining much, so we're not recharging the aquifer very much. But as long as we have this green here, that tells me we're pumping it out. So areas that have low rainfall have low recharge, and if we're pumping a lot of water out for irrigation practices, we have high rates of discharge. And here's your equation for how to deplete an aquifer. And deplete them we do. Most of the world's major aquifers are becoming depleted. A classic case, and you can find this all over the place. Classic case is the Central Valley of California, which is a major agricultural exporting area of America. And basically, you have this aquifer it's a very arid landscape, so there's not a lot of recharge happening, and there's a lot of farming happening, so people are pumping like crazy from here. All right, look at this. In 1925, this is where the land was. The dirt was here. Okay, it has experienced a thing called subsidence, land subsidence. As they pumped all this water out from underneath it, the land has sunk and sunk and sunk and sunk and sunk. So the San Joaquin Valley has sunk meters, over 10 meters, just in the last century, because of us pumping water out of it. So, and it sometimes makes sinkholes and other features like this. And we see this all over the world. We see it in China. We see it in Europe. We see it in all over the place, right? Where we pump water out of a aquifer faster than it can recharge. Don't be surprised if we get subsidence of the land as a consequence. Now, here's a map showing the world's major aquifers and showing which ones have higher rates of recharge versus depletion. So depletion just means you have higher discharge than recharge. And so what you can see is there's a couple of them that are actually recharging fairly fast. However, many of them are either not doing very well or actually hurting pretty significantly. Okay, and this problem is just going to continue because the world's population grows. We need more food, which means we need to pump more water. And so these aquifers are basically getting used up. Essentially, if you're depleting an aquifer, if you're pumping water out faster than it recharges, you're treating that water like a non-renewable resource. If you use it up faster than you get it back, it's non-renewable, right? Oil and coal are still being made; they just aren't made nearly fast enough to keep up with the rate at which we're using them. Same thing with water. Now, there's a very important aquifer in question that you'll hear about on the test. You should be prepared to hear about this one. So, in the United States, there is an aquifer known as the Ogallala Aquifer. And the Ogallala Aquifer occupies the central part of America, which is considered the breadbasket of America. So we have a lot of agricultural output. And this agricultural output has been possible because of this aquifer. This aquifer is mostly leftover water from when this used to be heavily glaciated in the Pleistocene 10,000 years ago. And as those glaciers melt, a lot of that water came into here. Now it's still getting recharged. It's not like this is only glacial water. It still gets recharged, but it gets recharged a lot slower than it's getting discharged. So here's a detailed map showing like where you're getting declines in terms of how many feet of decline there is. Okay, so you can see like this area where the well water, that used the well, the water was here in the well, the water has gone down in some places up to over 150 feet. That's a lot. Okay, that's like 50 meters. Okay, so there has been significant depletion of this Ogallala Aquifer, and they think basically by half a century from now, when you're my age, it'll be mostly gone. Okay, it's basically it's a non-renewable resource at this point, and that's a problem because it's a $35 billion a year industry here. This is where a lot of money is being made. And people want to make money. It's the tragedy of the commons all over again. Here's a common resource. We're treating it like it's just free. People don't want to take ownership of it, so they're just exploiting the heck out of it. You need the government to intervene. Now, so aquifers, they're used a lot, but actually most water comes, 2/3 of the water we use for agriculture comes from surface water, often from dams. So what people do is they'll build a barrier that basically blocks the flow of a river, and that will form a lake behind the dam. Now, so this accounts for about 70% of agricultural irrigation water comes from these features. Okay, these man-made features. Sometimes we just take it directly out of the river, but a lot of times we build these dams. So the idea is when we build a dam, we get several benefits out of it. Okay, first of all, and we'll talk about it separately because there's lots of environmental issues associated with dams, and we'll talk about that when we do energy. But the deal is this: you build this dam, and what happens is you can make electricity by spinning turbines. So you get clean, non carbon emitting energy for a long time, potentially indefinitely. Okay. All this water behind here now is available for agricultural purposes. You can pump this out. You can use it for municipal water. That means you can drink it. And also, we can use it for controlling floods. So if we're in an area where there's sometimes floods, well, we can control that water now. Like on the Tanchan, they control the water. They prevent flooding with it. Okay. Now, let's just do some simple math. Okay. All right. So pardon my artwork. It's not the best number, but let's just say I build a dam and I make this lake behind the dam. All right. I know it looks like a car or something, but this is supposed to be the lake behind the dam. All right. Now, let's just say the outflow from the dam is 50,000 liters a minute. I have no idea if that's an accurate number. I just made that up. Okay. Now, let's just say the inflow is 80,000 liters a minute. What's happening is I'm pumping 30,000 liters a minute out of it to water crops. Well, just think about it. If I'm taking water out for crops, then that has to mean that the rate of inflow is going to be greater than the rate of outflow because I extracted some of it. All right. And so what that means is the river got smaller rather than larger as it moved downstream. And usually, if we don't mess with the river, as it moves downstream, another river joins it, they get bigger and bigger and bigger. But as you build dams, they get smaller and smaller and smaller because every time you build a dam, you're going to pump some water out for, well, if you're pumping it out for agricultural purposes. You can also lose it to evaporation, but usually you're going to do some agriculture with it, right? Now, what happens then is pretty shocking. So take the case of the Colorado River. This is another one you should be prepared to talk about. The Colorado River runs through the western part of America, of the United States, and it comes out in the Gulf of California here, between Baja and the mainland of Mexico. And it has 15 dams built along it. This includes the Grand Canyon, by the way, Glen Canyon Dam, whatever. Okay. Now, again, we'll talk about dams later, but the point is, there's 15 dams along here, and there's a lot of agriculture done with it. Now, what happens is, so much water gets extracted from it that it got to the point where it doesn't even reach the sea most of the time. It just dries out. There's nothing left to go into the ocean. So this, I mean, there have been times when it does reach it, but for the most part, we pump so much water out of it for agriculture that there's none left to get to the ocean. Now, here's a classic one, and one they actually say you must know for the test. And it's a tragic one. It's one of the greatest environmental disasters ever. It's called the Aral Sea. Now, so the Aral Sea was actually a lake, uh, a type of lake that's below, that doesn't have an outflow. It doesn't flow out to the sea, so it's kind of like the Great Salt Lake or the Dead Sea. And so it had, but it wasn't that. It was a little bit saline, but not that saline. And it had a fishery. It was the world's fourth largest lake. Think about that, the fourth biggest lake in the world, and it had a fishery, and it was an important agricultural, an important economic feature of Kazakhstan. Well, what happened is the Soviet Union had control of the rivers that flow into it, and they're like, "Oh, we're just going to build some dams, and we're going to start pumping some water out and make this big mega farm area out of it," which they did. But they pumped like the Colorado River. They pumped so much water out of it, there was nothing left to go into the Aral Sea. And just look at these pictures. This is what it used to look like in 1977, and then we. What was this? What year is this? This is 86, 99. You can just see it. It just went away. We just pumped all the water out of that poor thing and dried it all up, killing all the fish. I mean, there's a little bit of it left, and they're trying to save what they can. But basically, it's a classic case uh, of people overusing a resource and causing an environmental problem that was an unintended consequence. And in this case, it hurt a country that wasn't the one of, well, actually, at the time, Kazakhstan was part of the Soviet Union. But for most of the time this was happening, it was just Russia at that point, right? But the point is, they basically destroyed this inland body of water in order to extract water for agricultural purposes. Look at these images. So now you just have like these. This used to be, an inland sea with fisheries, and we had these fishing boats, and now they're just sitting out in the middle of essentially a desert that was formed by the removal of all the water from the rivers leading into it. And let's talk about Egypt. Okay, so people in Egypt have been using the Nile as a source of irrigation water for 5,000 years. I mean, they have records. They have 5,000-year records, 3,000 BC records, where they talk about, it's like, here's how we build these canals, and here's the mechanisms we use for pumping the water out. And so I mean, if you ever have a chance to go to Egypt, it's amazing because it's just this land of just barren desert. And then there's just this bright green path going through the middle of it because there's all this water right along the banks of the Nile. Now, they didn't build dams. They just took water out of the Nile. And so it's still, to this day, if you look at it on Google Earth, it's just amazing, right? Now, they did build a dam on it in Aswan for power generation. It was in such a desert area that soils couldn't even support. I don't even think they pump water out of it for agriculture at all, as far as I'm aware, okay? But look what happened. You follow the river south, and you see this ribbon of green, right? Okay, but if you keep going, it's called the Blue Nile. So one of the sources of it is the Blue Nile down here. And in Ethiopia, they began building a thing called the Grand Ethiopian Resistance Dam, or GERD. Okay, and this is making Egypt really upset because it has greatly restricted the amount of water flowing into the Nile, which is affecting boat traffic, it's affecting irrigation, is restricting municipal water supply. So this is a classic water war that could spill into a real war because Egypt is a fairly powerful military, and they're really, really angry at Ethiopia for doing this. Now, Ethiopia, if you look, is kind of green. They don't really need the irrigation. They want it for power generation. And they say yeah, we're not going to restrict the flow of water in the Nile, but that doesn't seem to be the case. But the point is, it's a shared resource, and when the upstream people make use of it, it is the downstream people who suffer, and that is a classic water war that's happened quite a bit in different countries of the world. Well, let's talk about the Dead Sea. I hope you get a chance to see the Dead Sea. The Dead Sea is wild. I mean, it's this super saline body of water that's located. Oh, wait, I got to move this out of the way. Okay, here you can see it down here. Okay, here's the Dead Sea down here. Okay, this is the River Jordan. It winds through. It makes the border between Israel or occupied. What's it called? Occupied Palestine, okay? And then here is Jordan, okay? And you can see there's a lot of agricultural land here, right? Well, where's all this green coming from? It looks like a desert to me. Well, they're pumping it out of this river. And so, again, this river gets so used that by the time it reaches the Dead Sea, there's nothing left. It's like the Colorado River. It's like the river flowing into the Aral. It runs out of water because it's being used to irrigate. Well, a consequence of that is the Dead Sea is dying because it needed some input, but it's not getting it. So the Dead Sea is shrinking because of all the agricultural use of the water in the Jordan River. Now, as it dries out, a weird thing happens. So, like the shoreline has receded, like in some cases over a kilometer. My wife and I went there, and we thought there's one resort, and they're like, you can't go to the Dead Sea anymore. It's like, yeah, we used to be a Dead Sea resort, but now it's like it's a kilometer out there, and you can't walk there because of these. What happens is this is a hypersaline environment, so there's a lot of thick salt deposits under here. And even though it's a desert, it still rains sometimes. And when it rains, it dissolves the salt and it becomes unstable. And these holes fall in, and people have died by falling into these things. So I mean, it's a tragedy because the Dead Sea is one of those really cool parts of the world that everybody should get a chance to see. And again, it's this shared resource. Nobody wants to take ownership of what they're doing, and as a result, it's like now there are plans in place to try to salvage it, but we'll see. That's not really what we're talking about today. But let's talk about Israel a little bit more. So Israel is a country that's basically in a desert, and like they actually have a lot of agriculture for. So here's what they used to have. They had Lake Kinneret, otherwise known as the Sea of Galilee. They had a mountain aquifer, and they had a coastal aquifer. We'll talk about what happens when you pump water out of coastal aquifers in just a little bit. But like many parts of the world, they're experiencing a mega drought, and this mega drought has been going on for like a long time, like centuries actually. And as a consequence, their water has become very scarce. They ran out of water, they ran out of food, they don't have a lot of friends in the surrounding countries. It could be really bad. All right. So Israel had to figure out what to do. And what they came up with was pretty cool. They said, you know what? We've got lots of seawater. We're on the Mediterranean. That's water. So let's turn it into fresh water. So normally, the sun lifts water molecules out of the ocean in the water cycle and drops it as fresh water on the land, where it can either infiltrate and become groundwater or become runoff and join streams. But it's the solar energy is what's basically desalinating the water. Well, what they do is they say, well, there's mechanical methods we can employ to do the same thing. Rather than boiling it, we'll use a different method. So it turns out now this factory here produces 55% of the water in Israel. Israel went from being a water poor country to a country that actually exports water and sells it to countries in the area. They use a process called reverse osmosis. My son, who works on a ship, they're out at sea for months at a time. They need water. They make it out of seawater using this process called reverse osmosis. And it's a really simple idea. You have a semi-permeable membrane, kind of like the membrane of an egg, right? And what you do is you push water under pressure into it. And so you're forcing water under pressure, salt water, through this membrane. And this membrane lets water molecules through, but it doesn't let through salt ions. So what comes out is fresh water. All right, now it's amazing, right? All you had to do is force water under pressure through this membrane. It's called reverse osmosis. Now the thing is, though, that it takes energy to do that, and so what we find is that facilities like this one they have here, that yes, I can pump water in from the Mediterranean. I can put it through my reverse osmosis system. I can get this fresh water out. I can sell some of it to my neighbors. I can put the saltier stuff back in the ocean, no problem. But here's the thing. It takes energy, right? So I'm basically having to burn fossil fuel or build a nuclear plant. Okay, but it takes energy to run these things, quite a bit of it. So it takes energy to separate water from salt. So you can either use the sun doing it for free, or if that's not doing it for you, you can use a desalinization plant. But actually, this might be something that could be quite useful, especially in supplying municipal water for people around the world in places that are experiencing droughts. Last thing I want to talk about. Sorry, this is a long one. I want to talk about saltwater intrusion. So groundwater is really special. Aquifers are precious. You do not want to lose an aquifer. You don't want to drain them all the way down, but even if you do, they'll recharge in time, right? What you don't want to do is lose one through saltwater intrusion. So in coastal areas, like say Israel, here's what you've got. You have this aquifer. And normally, remember, water is flowing in an aquifer downhill. So the water in the aquifer would be flowing this way. Let's say I turned off all these production wells. Okay, the water would just flow this way and go into the Mediterranean Sea. And you can see down here, it's basically by flowing this way, it kind of holds back the salt water. Okay, so salt water, like regular water, also wants to flow into the ground, right? And so what happens is the outflow of this water holds that salt water back, so that the water in these wells is fresh water. But what happens if we start pumping water out of these? Okay, let's just see what happens. As I start pumping water out of here, what's going to happen is that boundary between the salt water and the fresh water is going to, if I take fresh water out, if water is starting to move this way, then the salt water starts moving this way, and we call that saltwater intrusion. Okay. And in fact, eventually what will happen is this well here will become contaminated. And once that happens, you will never get the salt out. You'll never be able to use that again. Like that, once you salinate an aquifer, in the history of the future history of humanity, will not be enough time to get that salt out. It's ruined. And so that's why you've got to be really careful in how much production you have out of wells that are near the ocean. So basically, this one I think shows it pretty well. So let's say I have a well here. Normally, the water would be flowing this way, and it'd be holding the water right here. So the salt water freshwater interface would be right here near the ocean as this water flows out. But what happens is, as this well starts pumping water, it's going to this interface is going to start moving to here, and then it's going to move to here, and it's going to move to here, and now my well is pumping salt water, and the well's no good anymore. But not only is that well no good anymore, all this area here, all this aquifer here, useless. So that's saltwater intrusion. I think that's our whole show. I'm sorry it took me so long to get through this, but these are important topics. Thank you for listening. Oh, there it is. Oh, darn, what did I just do? No, now I don't know how to stop. How do I stop? Maybe I do this. Do I do this? I don't know what I'm doing. Oh no, let's try this. This is embarrassing. Okay, here we go. It looks like a stop button now.